Through the 2014 paper 2 for pure mathematics, unit 1. And it says, let P, Q, and R be three propositions. Construct the truth table for P implies Q and R implies Q. So you're going to construct a truth table for P implies Q and R implies Q. So to construct this truth table for P implies Q and R implies Q, first thing we have to notice that there are three variables. All right, there's three variables. Since there are three variables, then the number of possible outcomes is 2 cubed. 2 cubed is 8. All right, so the first thing we're going to do is set up your table. All right, so let's set up our table. And the variables again we know are P, Q, and R. All right, nice. So now let's put in the outcomes. We know that we're gonna have for P it's gonna be 4 true and 4 false. All right, so you can write the 4 true first, then you write the 4 false. You don't have to use true and false. You can use ones and zeros. A lot of people like to use ones and zeros. 1 representing true and 0 representing false. So that's for P. Then for Q, it's going to be true, true, then false, false, then true, true, then false, false. That gives the 8th possibility for Q. Nice and easy. Then for R now, it's going to be true, false, true, false, true, false, true, false. True, false, true, false, true, false, and true, false. Nice and easy, soft. Now, based on the question, remember, this is what we need to draw the truth table for. So before we can do that, we need to construct the truth table for what is P implies Q, and then we're going to need R implies Q. All right, and after we get these now, then and only then we can be able to look at what's the truth result for the two of them together. P implies Q and R implies Q. So we look at that afterwards. So now P, let's go here now. Now P implies Q, let's put the results them in red. P implies Q, the only time it's gonna be false is when P is true but Q is false. So you're gonna look for when P is Q but Q is false. That's somewhere right here. P is true and Q is false. Here so as well, P is true and Q is false. So these are the only two times when P implies Q is going to be false. Everywhere else it is true. All right, everywhere else it is true. So you can just put true, 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 and true. Nice. Then for R implies Q, the only time it's going to be false is when R is true and Q is false. So R is true and Q is false. R is true and Q is false. So right here again, R is true and Q is false. R is true and Q is false. So these are the only two places. All right. So let's write that it's going to be false here and it's going to be false here. Everywhere else is true. This is true, 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 and true. Finally, what we're asked to draw a truth table for is actually P implies Q and R implies Q. This is what we want. So we need and of these two. We need and of these two. So what that is going to be is true and true is true. True and true is true. False and false is false. True and false is false. True and true is true. True and true is true. False and true is false. True and true is true. All right? And so this is the answer. Nice and easy, and you get your 5 marks. No issues. Soft. Let's go to the next part of the question. The next part of the question says a binary operator is defined by, I don't know what that is. We can just call it circle plus. A binary operator is defined by circle plus, and they are telling us that y circle plus x is equal to y cubed plus x cubed plus ay squared plus ax squared minus 5y minus 5x plus 16. Right? And it says state given reason for your answer if y, if circle plus is commutative. So again, it tells us that, let's write down what it tells us. It tells us that y circle plus x is equal to y circle plus x is equal to y cube plus x cube plus ay squared plus ax squared minus 5y minus 5x plus 16. Now to show if it is commutative, there are many ways you can do it, but ultimately you want to show that y circle plus x is equal to x circle plus y. So you can even give it some values, right? You can probably let y equal 1 and maybe x equal 2, right? Just give it some value. If y equal 1 and x equal 2, what you get is 1 circle plus 2. 1 circle plus 2 is equal to 1 circle plus 2 would be 1 cube, which is 1, plus 2 cube, which is 8, plus a times y squared is 1, so it just becomes plus a, plus this becomes 2 squared is 4, that becomes 4a, minus 5, minus 10, plus 16. And so what you get is 1 circle plus 2 works out to be 1 plus 8 is 9, 9 minus 5, 9 minus 5 is 4, 4 minus 10. Let me see that. 4 minus 10 is negative 6 plus 16 is 10. So 1 circle plus 2 give you 10. Now, if you can show that 2 circle plus 1, if this give 10, then clearly commutative. So this is just proving it using an example. So 2 circle plus 1, right? 2 circle plus 1, you would see that you would get 2 cube is 8 plus 1 plus ay square. Ay square is going to be 4a plus ax squared is plus a. I know what you're saying. I forgot to say 10 plus 5a. I know. I don't know why I left off the 5a. 10 plus 5a minus 5y, which is minus 10, minus 5 times 1, which is 5, plus 16. And this still works out to be 10 plus a. Right? Now these are the same. These are the same. These are the same values that we're getting. So since we're getting the same values, you can conclude that y circle plus x, that's what I call this binary operator, y circle plus x, it's equal to x circle plus y based on our example, right? And it doesn't matter which number you choose, it's going to be the same, all right? And so circle plus is, so therefore circle plus is commutative. So that's how you show that. Nice and easy, soft. So that's the first part. You didn't have to actually use examples. You could have just used x and y itself. But it looks trivial to me that way. Now the second part says, given that f of x is 2 circle plus x, f of x is 2 circle plus x, and x minus 1 is a factor, find the value of a. So they're telling us that f of x is equal to 2 circle plus x. So if f of x is 2 circle plus x, what we're doing is we're going to replace y with 2. Anywhere y is, we replace it with 2. So y, 2 cubed is 8, plus x cubed, 2 square is 4, so that becomes plus 4. Let me see, 2 square is 4, that becomes plus 4a, plus x, a x squared, and replace y with 2 again, you get minus 10, and minus 10 right here. But minus 10 plus 16, I'm just going to put plus 6, minus 5x. Now you can go further and simplify this by saying that this is equal to 8 plus 16. 8 plus 6 is 14. So we can rewrite this in the form that this is actually x cubed plus ax squared, x cubed plus ax squared. Where's our x term now? Minus 5x plus 14 plus 4a. All right, would have need some space. So let's not quinge it up right there. Let's make some space. So we're saying f of x is actually x cubed. We're just going to arrange it in descending powers of x. So we have x cubed plus ax squared minus 5x plus, now 8 plus 6, 8 plus 6 is 14. So you get plus 14 plus 4a. All right, nice and easy, soft. Then what was the next question that they asked, or they said? The next bit of information is that they said that x minus 1 is a factor. If x minus 1 is a factor, then they're telling us that f of 1 is equal to 0. If f of 1 is equal to 0, then that implies that we can put in 1 cube and get 1 plus a. So we're going to get 1 plus a minus 5 plus 14 plus 4a and 4 plus 4a, and that is equal to 0. Nice. Just make sure putting everything correct. 1 cube is 1. 1 square. That's good. Minus 5. This is 5. Now 1a plus 4a is 5a. So this implies that 5a is equal to, we're going to bring everything over to the other side. 1 minus 5 is minus 4. And minus 4 plus 4t, that is 10. So when we bring everything to the other side, 5a is equal to minus 10. And so a is equal to negative. Divide through by 5, a is negative 2. So that's the answer. All right, so this was the first part. This is the next part. A is minus 2. Easy, soft. Now let's go ahead and look at the next part of the question. Next part says factorize f of x completely. Given that we know the value for a now, we can rewrite f of x as f of x is going to be equal to x cubed, and it was plus ax squared, and a is minus 2, so it's actually minus 2x squared. So that's minus 2x squared. Then we have minus 5x plus 14 plus 4a, but 4 times minus 2 is minus 8. 14 minus 8 is 6. So it's really just plus 6. All right, nice and easy. Now, you could go ahead and use factor and remainder theorem and factorize this, but this is what I'm going to do. All right, this is what I'm going to do. I'm just going to factorize them in one go. How do I do that? Let's find out. They told us that x minus 1 is a factor. All right, I'm going to factorize it in one go. Now, I need the other two roots. I know this has to be x and x. I know that the sum of the roots need to be 2 and the product need to be 6. So the next two roots I need, when I multiply the 3 roots, if one root is 1 root should be something here and another root here. I know that the product of them should be 6. So let's say I call this root, root A and B, right? Then I know say A times B times 1 must equal to minus D over A, which is negative 6. All right? And then I know that when I add the 3 of them, I know that when I add all of them, I know that I'm supposed to get 1 plus A plus B. Yes, 1 plus A plus B. I know that the sum of the 3 roots is going to be 2. So what A and B must be, man? Let's try 3 and negative 2. So we're going to just try. So trying 3 and negative 2. 1 plus 3 is 4. Bingo. Plus minus 2 is 2. So 3 and negative 2 works. 3 and negative 2 works. So good. Yep. So the other roots are, so just writing them down, that the roots are, so not all the time you need to be doing that polynomial division. So the roots are 1, 3, and negative 2. Right? So now we can write the factors. It's going to be x minus 3 times x plus 2. That is it. And you can check it. You add up the roots. 1 plus 3, 1 plus 3 plus minus 2. That should give you 2. When you check it, the product of the 3 roots will give you minus 5. You can check it. So that means the product by 2, that means 1 times 3 plus 1 times minus 2 plus 3 times minus 2, that it will give you minus 5. So not all the time you need to be doing polynomial division, right? Just use sums and products of roots. So that takes care of part B. This is part B. Tired of just factorizing every time. Every time people are just factorizing. Why you want to be factorizing all the time with polynomial division? Now let's look at part C. Part C is a proof by mathematical induction, and it wants us to prove that 1 square plus 3 square plus 5 square plus blah 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 plus 2 to the n minus 1 square is n over 3 times 4n square minus 1. So all of that, you can call it maybe a statement Pn, and Pn is a statement such that we're summing from r equal 1 to n of 2r minus 1 all squared. You don't have to use the letter r as a dummy variable. You can use t, you can use s, anything, but you will commonly use r. We stick with r, and that's equal to n over 3 times 4n squared minus 1. So now let's get it. So now we're going to start with when n is equal to 1. All right, when n is equal to 1, when n is equal to 1, what we're going to get is the left-hand side becomes, your left-hand side is just the sum from r equal 1 to 1 of 2r minus 1 square, and all of this just works out to be 1 square, which is 1. All of this works out to be 1 square, and 1 square is equal to 1. All right, this is step 1. All right, then your right hand side is going to be equal to, when you put n as 1 in the right hand side, you're going to get 1 over 3 into 4 times 1 square is 4 minus 1, and so 1 over 3 times 4 minus 1, that is going to be 3 over 3, and 3 over 3 is 1. So good there. So again, so therefore we can conclude, therefore P1 is true. So P1 is true. Now that P1 is true, we need to show that we need to assume Pn is true. And so when n equal k now, that's step 2, when n is equal to k, so let n equal k. So now that we let n equal k, all right, now that we let n equal k, we're just saying that the statement is going to become the sum from r equal 1 to k, sum from r equal 1 to k of 2r minus 1 square. And this is equal to n over k over 3 into 4k squared minus 1. And we're going to assume that n equal k is true. All right, that's with n equal k. This stage you assume. So you're going to assume n equal to k is true. Assume that this step is true. So since we assume that it is true, we're just assuming. Now step 3. Now we need to show that n equal k plus 1 is true if n equal k is true. All right, so let n equal k plus 1 now. So when you let n is equal to k plus 1, this is what we are going to get. When n is equal to k plus 1, we're pretty much asking to find the sum from r equal 1 to k plus 1. The sum from r equal 1 to k plus 1 of 2r minus 1 all square and the sum from r equal 1 to k plus 1 is equal to the sum from 1 to k, and the sum from 1 to k is this. The sum from 1 to k, which is k over 3 times 4k squared minus 1 plus the k plus 1 term. How do we get the k plus 1 term? We'll go in here and replace r with k plus 1. So that's going to become 2 times k plus 1, 2 times k plus 1 minus 1 all squared. Nice and easy, soft. And we need to simplify out this now. All right, now this is really 2k plus 1. All of this is really 2k plus 1. So let's write that. All of this is really k over 3. This is really k over 3 into 4k squared minus 1 plus this part is really 2k. This is really 2k plus 1 all square. That's what we have, 2k plus 1 all square. All right. Now look what I'm going to do. Since I have a k over 3 right here, right, which looks, I want to have a 3 over 3 right here. So let me put it in a different color. You might say, so sir, why are you putting a 3 over 3 right there? Well, I'm putting a 3 over 3 right here, so it looks easier for me to factor out 1 over 3. That's the first thing I'm going to do. Let's do that around here. I'm going to factor out 1 out of 3. So what we're finally getting now is the sum from r equal 1 to k plus 1 of 2r minus 1 all square is going to be equal to, we're going to factor out 1 out of 3. We're going to factor out 1 out of 3, and we're going to be left back with, factoring out 1 out of 3, we're going to have k times 4k squared minus 1. We're going to have k times 4k squared, k times 4k squared minus 1. All right, and that is plus. When I factor out 1 over 3, I'm left back with 3 times 2k plus 1 all squared. That's what I have. Nice and easy. So what do I do next? I continue. So I have 1 over 3 into, all you're going to do now is expand inside this bracket. K times 4k squared is 4k cubed. Then k times minus 1 is minus k. Plus 3 times, now I need to expand what is 2k plus 1 all square. 2k plus 1 all square is first term square. So 2k square is going to be 4k square. Plus twice the product of the two, which is plus 4k, plus second term square, which is plus 1. Cool. So that's what we get. So now we can do one more, expanding in the bracket to get, this is going to be equal to 1 over 3 into, it's 1 over 3 into 4k cubed. So we have 4k cubed minus k plus, no, 3 times 4k squared, that's going to be 12k squared. So we're getting 12k squared plus 12k plus 3. 12k squared plus 12k plus 3. Nice and easy. Now the only thing that we're going to do now is put this together in one pretty frame. We're going to put it together nice and pretty, and we're going to write it as 1 over 3. We're going to write it as 1 over 3 times 4k cubed. Then group up our k square terms together. Grouping our k square terms together, it looks like it's just the plus 12k square. Then we're going to group our k terms together. Grouping our k terms together, notice we have a minus k and a plus 12k, so that's 11k. So we get plus 11k. And then what do we have left? We have just our constant, which is plus 3. All right, nice. So we have 4k cubed plus 12k square plus 11k plus 3. All right. Now remember, what are we trying to get? What's the goal? The goal is to show that the sum from 1 to k plus 1 should be k plus 1 over 3 times 4 times k plus 1 all square minus 1. All right, we need to get this to be k plus 1 over 3 times 4 into k plus 1 all square minus 1. So that means we need to factor out k plus 1 out of this. The only way we can factor out k plus 1 out of this is doing polynomial division. Yes, I know it is tedious, but we're going to have to do it. So we're going to do that to the side in red. We're going to do a polynomial division. We're going to factor out k plus 1. We're going to factor out k plus 1. Factoring out k plus 1 out of 4k cubed plus 12k square plus 11k plus 3. K into 4k cubed leave 4k square. 4k square times k is 4k cubed. 4k square times 1 is just 4k square. Then we're going to subtract these two statements from each other. Subtracting them. When we subtract, always put a bracket before you do your subtraction. You subtract them, you're going to get 12k square minus 4k square is 8k square. Because the 4k cubes cancel, so you have 8k square plus 11k. And then k into 8k square, that's just going to be plus 8k. And then you're going to go 8k times k plus 1. That's going to be 8k times k is 8k square. That's 8k square plus 8k times 1 is 8k. And then we're going to do some subtracting. When we subtract them now, we have 11k minus 8k is 3k. So we have 3k plus 3. Good. So we have 3k plus 3. Then we have k into 3k. That just leaves k into 3k. That just leaves plus 3. And then k times 3 is 3k. That's 3k plus 3. When you do the subtraction, clearly you're going to get 0. We don't even need to work it out. Clearly, we're going to get 0. All right, don't even need to work that out. We know that that is 0. No issues with that. All right, we know that's 0. So what does that tell us? That tells us then that we can rewrite this now as 1 over 3. Let me separate these pages. Let me separate this. That's just a rough work. You don't really need this in part of your solution. It's just rough work. All right, this is not necessarily a part of the solution. This is rough work. So this becomes 1 over 3 times, it becomes k plus 1 times, becomes k plus 1 times 4k squared plus 8k plus 3. Now when you get to this stage, now you can actually factor out the k plus 1. Now you're going to factor out the k plus 1 to say this is now factor out the k plus 1. It becomes k plus 1 over 3 times, and you're left back with what's inside the bracket, which is your 4k squared plus 8k plus 3. But remember, this is not how we want it. We don't want to leave it as 4k squared plus 8k plus 3. What are we trying to generate? We're trying to generate, this is what we're trying to generate. We're trying to generate 4 times k plus 1 all square. 4 times k plus 1 all square minus 1. So now I'm going to do some rough work again on the side. I'm going to show you this. What is k plus 1 all square? So this is some more rough work. K plus 1 all square, you're just showing them this. K plus 1 all square, doing some rough work. That is k squared plus 2k plus 1. Alright, this is rough work again. Now, if you were to multiply this by 4, let's say if you multiply this by 4, it would become 4k squared plus 8k plus 4. And so if you were to then subtract 1 from it, then this would just become plus 3. So look. What are we then saying? See there? 4k plus 1 all square minus 1 is equal to 4k squared plus 8k plus 3. So we can replace all of this with that. So we can say all of this is actually just equal to k plus 1 over 3 times, we can write it now that all of that is 4 times k plus 1 all square minus 1. Four times k plus 1 all square minus 1. So therefore, you can conclude now, therefore, pk plus 1 is true. Because we call the statement pn, so therefore, pk plus 1 is true. Now, generally, when you finish, you don't just done this. So always write a conclusion. Always write a conclusion. Always write a conclusion that hence, by mathematical induction, hence by come by to write out that long word, hence by PMI, the statement above is true for all natural numbers. That's your conclusion. This is step 4. Always write your conclusion. Always write your conclusion. Always. All right, that's the conclusion. Hence, by PMI, the statement above is true for all natural numbers. Question 1, soft. All right, question 2 now. Question 2 give us a function f of x, and it says f of x is 2x squared plus 1. So this is your function f of x, and they tell you that f of x is equal to 2x squared plus 1. So if f of x is 2x squared plus 1, what do? They're asking us to find f square x. Now, f square x doesn't mean you square this. F square x means f of x. It means you put f into f. You put f into f. That's f square x. So putting f into x, it really means f of x. All right. So putting f of x into f, we're going to get 2 times 2x squared plus 1 plus 1. So when you simplify this, it's going to be 2 times 2x squared is going to be 4x squared. And then 2 times 1 is 2 plus 1 is 3. So it's 4x squared plus 3. That's f of x. The next thing they're asking you for is fg of x. So let's write what g of x is up here. They're telling us that g of x is equal to x minus 1 over 2 square rooted. So we've done part A. Part B, we want to find fg of x. Now, fg of x means that you put g of x into f. Fg of x means you put g of x into f. So putting g of x into f, we're going to get 2 times x squared. You're going to replace x with all of that. So you're going to replace x with the square root of x minus 1 over 2 all squared plus 1. When we work that out, what we're going to get is the square cancels the square root, and so we're just left back with 2 times x minus 1 over 2. It works out to just be now 2 times x minus 1 over 2 plus 1. So this works out to be the 2 cancels the 2 here. This 2 cancels this 2. And then x minus 1 plus x is just x. So fg of x is x. Nice and easy. Soft. All right. So if fg of x is equal to x, then what does that mean? That is telling us then that the two functions are inverse of each other. So we can state that this, hence or otherwise state the relationship between f and g. So in the second part, we can tell them f and g are inverse functions of each other. That is, f is the inverse of g and g is the inverse of f. All right, so you can tell them that they are inverse of each other. Nice and easy, that's part 2. Now let's go to part B now. Part B says, given that a cube plus b cube plus 3a squared b, so let's write that down. They're telling us that a cube plus b cube plus 3a squared b, and they're telling us that that is equal to 5ab squared. 5ab squared. And then we need to use that to show that the 3 times the log of a plus b over 2 is equal to log a plus 2 log b. Now, before we do this, before we even look at this given part, I want you to first just analyze this, what they have. Let's write it down in red, because this is not a part of the question. This is just jottings. You have 3 log a plus b, 3 log a plus b over 2, right? By laws of logarithm, really and truly, this is just the log of a plus b over 2 all cube. That's just the log of a plus b over 2 all cubed. This is in reality what we have, the log of a plus b over 2 all cubed. So if this is what we have in reality, the log of a plus b over 2 all cubed, Let's try to work out what a plus b over 2 cube is, and then do this some sort of substitution and see if it will give us the actual answer that we want. All right. What do I mean by that? What I mean is I'm going to generate a plus b over 2 all cube, and then try to find what the log of that is and see if I'll get the answer that they want. So this is just jottings. All right. So first thing I'm going to start with is what is a plus b over, let me put it in black. We don't even need to put it in black. Let's change that color to burgundy. So we have a cube plus b cube, right? A cube plus b cube plus 3a squared, all of that is 5a, blah, blah, blah. And we're going to start with this. So in order to start with that, first thing I want to tell you is that a plus b all cubed over 2 cube, and we know that 2 cube is 8, don't it? And so what we really have is that this is really and truly a plus b all cubed over 2. So let's just put in the 2 and write it as a plus b over 2 all cubed. All right, so this is equal to a plus b over 2 all cubed. All right, and in reality, this is just a plus b all cubed over 8. Now, the next thing that is coming to my mind is expanding. I know how to expand a plus b. I know to expand a plus b all cubed. All right, I know how to expand a plus b all cubed. So I'm not going to expand this one, and I'm expanding this one. I'm expanding this one. I know that a plus b all cubed is a cube plus 3a squared, 3a squared b plus 3ab squared plus b cubed. And all of that is divided by 2 cubed, which is 8. Now, as you can see, guys, look at this now. Let me put this in black. Here I have a cubed, I have 3a squared, this part, plus this b cubed. All of this part together is going to work out to be equal to, those three together is this, 5ab squared. So now I get 5ab squared plus, this is now 3ab squared over 8. Now 5ab squared plus 3ab squared over 8 is just ab squared. That part works out to just be ab squared. So what can we conclude, guys? We can conclude that a plus b over 2 all cubed, a plus b over 2 all cubed, we can conclude that that is equal to a b squared. That's what we can conclude. How did I come up with that conclusion? Here it is. A plus b over 2 all cubed is the same as ab squared, right? So now if these two are equal, we can take the log of both sides now. We can take the log of both sides to say that hence the log of a plus b over 2 all cubed is going to be equal to the log of ab squared. So if the log of a plus b over 2 all cubed is equal to log of ab squared, then what that means is if I carry down the power now, that means that 3 times the log of a plus b over 2, 3 times the log of a plus b over 2 must be equal to, I can separate this now as the log of A plus the log of B squared. This is the log of A times the log of B squared. Nice. Now this part I can go even further to break it down now as log A plus 2 log B. And that is equal to this over here, which is 3 log A plus B over 2. Nice and easy. So this is what we have solved. All right, so this is the proof of it. Nice and easy, solved. You can write proven. No, you didn't have to do it this way. No, you didn't have to do it this way. All right, there's also alternative methods, such as maybe you could have started by, I know that you would have learned sums and products of roots, and you'd have learned that A cube plus B cube. I think they teach you these formulas. They teach everyone these formulas, that A cube plus B cube is A plus B all cubed minus 3AB into A plus B. This is generally what is taught, right? And then the question I told you that A cube plus B cube, right? And then what you could do is the question I told you that A cube plus B cube plus 3A squared B equal 5AB squared could have then brought over this 3A squared B to say that, okay, well, A cube plus B cube is going to be equal to 5AB squared minus 3A squared B. You're wondering, how did I get that? All I did was make A cube plus B cube the subject from what is given. So bring over this. All right. So I would have gotten that, and that's equal to A plus B all cubed. This is equal to A plus B all cubed minus 3A squared B plus 3A squared B plus 3AB squared, sorry. And minus and plus give you minus. This should be minus. All right. Then what you could go further to do is bring over these two over here. By bringing over these two, bringing over this minus 3A squared to over here, it's going to become plus, and so these two cancel each other. This cancel this, and both this cancel this on this side, and then bringing over that becomes minus 3AB squared plus 5AB squared becomes 8AB squared. And that's going to be equal to A plus B all cubed. And then when you have this part now, you can divide both sides by 8. When you divide both sides by 8, you're going to end up get that AB squared is equal to, now 8 is 2 cubed, so it really works out to be A plus B over 2 all cubed. And then when you get to this side, you can just log both sides to say, oh, the log of A plus 2 log B is indeed equal to, carry down the power 3 to get 3 log A plus B over 2. So that's what you could do. This is an alternate method. You don't have to do this. My approach is using the traditional method over here. And so this is our method. Depends on how you like to do things. Depends on how you see things. You could even do it other methods, but I'm just showing you the two methods I would implement. Next part of the question. Now, the next part of the question, it says that solve each of the following equations. So we have equations to solve. These are the nicest things to do when you're just solving an equation. It feels like primary school again. You have e to the x plus 1 over e to the x. And you're solving this equation, e to the x plus 1 over e to the x minus 2. And you're solving this equal to 0. Since we're solving this equation equal to 0, we can multiply through by e to the x. By multiplying through by e to the x, we're going to get that this becomes e to the x squared. E to the x times e to the x is e to the x squared plus 1 minus 2 e to the x. And that's equal to 0. So this is now just a quadratic equation in e. So you can just write it in the proper order. This is just e to the x all squared minus 2 times e to the x plus 1 minus 2 times e to the x plus 1, and this is equal to 0. Now when you get to this stage now, you can go further to factorize. You can go further to factorize now, and you can say, well, e to the x squared, in order for that to be e to the x squared, it has to be e to the x multiplied by e to the x. And this is plus 1, so it's going to be a 1 here and a 1 here. Signs are the same, both of them negative, so minus, minus. And so what you're getting is that e to the x is equal to 1. If e to the x equal to 1, then x must be 0. So that's the solution. X is equal to 0. Anything to the 0 power is 1. So that's the answer. And if you don't believe the answer, you can check it. Put x as 0 in here. So you get 1 plus 1, which is 2. 2 minus 2 is 0. So that's a baby question, right? You don't even need to work it out, because you could just look at it and say x must be 0, like without working it out. Like, that's crazy. Let's look at the next part now. The next part is a log question. This is now logarithms, and this log part of the question, it is telling us that we have log to base 2 of x plus 1, log to base 2 of x plus 1 minus log to base 2 of 3x plus 1 and they're telling us that this is equal to 2. All right, log to base 2 of x plus 1 minus log to base 2 of 3x plus 1, they're telling us that that is equal to 2. Now, since that is so, this implies that log to base 2, of, we can join them together as 1. This is really telling us that log to base 2 of x plus 1 over 3x plus 1 is equal to 2. That's what that is telling us. That is what that is telling us. Since that is what that is telling us, now remember, the log of a base of a number is equal to a power. And so then this is telling us that 2 squared is 4. And so we can then conclude that x plus 1 over 3x plus 1 is equal to 2 squared by laws of logarithm. This is equal to 2 squared. All right, that's equal to 2 squared. So we can cross multiply We can cross multiply now to get that x plus 1 is equal to 4 times 3x plus 1. X plus 1 is equal to 4 times 3x plus 1. And then we're going to solve for x. So expanding through, you're going to get that this is 12x. And then 4 times 1, that becomes plus 4. And then over here we have x plus 1. So we need x's on one side. So I'm going to bring this x over here to make it 11x. And I'm going to bring this 4 over here to make it 1 minus 4 is negative 3. Then I divide through by 11 to get x is negative 3 over 11. That's the answer. X is negative 3 over 11. Soft. With a capital T. X is negative 3 over 11. Nice. Now let's look at part D. Part D says, without the use of a calculator, show that the root of 3 minus 1 over the root of 3 plus 1 plus the root of 3 plus 1 over the root of 3 minus 1 plus the root of 2 minus 1 over the root of 2 plus 1 plus the root of 2 plus 1 over the root of 2 minus 1 is 10. Now, all of that is too repetitive. Look what I'm going to do. First thing, I'm going to rationalize them one by one. You might say, that's crazy. Why would you want to rationalize them one by one? Just look why. I know that we have root 3 minus 1 over root 3 plus 1. All right? That's what we have first. If I can just rationalize this one first by multiplying by multiplied by the conjugate of the denominator. So I'm going to multiply it by root 3 minus 1 over root 3 minus 1. When I do that, I'm going to get, this is going to work out to be root 3 times root 3 is 3. All right, root 3 times minus 1 is minus root 3. Minus root 3, that's minus 2 root 3. That's minus 2 root 3. And then minus 1 times minus 1 is plus 1. Cool. Then we're dividing that by root 3 times root 3 is 3. Well, this is just the difference of 2 squared in the denominator now. So it's just a squared minus b squared. So this part just works out to be 3 minus, that works out to be 3 minus 1. 3 minus 1 is 2. So all of this is working out to be 3 plus 1 is 4. That works out to be 4 plus, works out to be 4, not plus, 4 minus 2 root 3 over 2. And then I do the division, and then I'm going to get 4 over 2 is 2, which is going to be 2 minus 2 root 3 over 2 is just minus root 3. So now I have 2 minus root 3. All right. Now the next one is that I'm going to have to worry about is root 3 plus 1 over root 3 minus 1. Now I realize that all of this is just the inverse of this. Notice that root 3 plus 1 over root 3 minus 1, that's just the inverse of this. So I could actually just write that this is going to be 1 over 2 minus root 3. If you see that, can you see that? Yep. Think of it. If this was A and this was B, this is A over B. And this would just be B over A. So this must be equal to 1 over 2 minus root 3. This must be equal to 1 over 2 minus root 3. All right. And then I can actually rationalize this. You can rationalize this part by multiplying this by 2 plus root 3 over 2 plus root 3. All right, so when I do that now, what I'm going to get is 2 plus root 3 divided by, this again becomes the difference of 2 squared. It's a squared, 2 squared is 4, minus b squared, which is minus 3. So this answer just works out to be 2 plus root 3. Nice. We're almost there, we're almost there. Now I need to work out what is the root of 2 minus 1 over the root of 2 plus 1. Root of 2 minus 1 over the root of 2 plus 1. All I'm going to do again is multiply by the conjugate of the denominator. What is the conjugate of the denominator? The conjugate of the denominator is root 2 minus 1 over root 2 minus 1. And I multiply by the conjugate of the denominator, it becomes root 2 times root 2 is 2 minus 2 root 2 plus 1. That's what I get when I work out the numerator. Nice. Then in the denominator, I get the difference of 2 squared, which is just 2 minus 1. And so all of this works out to just be 3 minus 2 root 2. And so now finally I need to work out what is root 2 plus 1 over root 2 minus 1. Now I can tell you that root 2 plus 1 over root 2 minus 1, we know that that is just the reciprocal of this, and the reciprocal of this is the reciprocal of this. And so this is just 1 over 3 minus 2 root 2. So all I need to do is multiply by the conjugate of 3 minus 2 root 2, which is 3 plus 2 root 2 over 3 plus 2 root 2. So what do I get? I get that this works out to be equal to, that in the numerator works out to be 3 plus 2 root 2 over the difference of 2 squared is 3 squared minus, which is 9, minus 2 root 2 squared, which is 8. And so that just works out to be 3 plus 2 root 2. So good now, really good, we're nice. So now finally I can add up all of these. Finally, we can add up all of these right here. So now we can write that the root of 3 minus 1 over the root of 3 plus 1 plus the root of 3 plus 1 over the root of 3 minus 1 plus the root of 2 minus 1 over the root of 2 plus 1 plus the root of 2 plus 1 over the root of 2 minus 1 all of this is going to be equal to 2 minus root 3. So let's bracket them. The first one is 2 minus root 3. 2 minus root 3 plus 2 plus root 3. 2 minus root 3 plus 2 plus root 3 plus, that's now 3 minus 2 root 2. 3 minus 2 root 2 plus 3 plus 2 root 2 as you can see right here, 2 plus 2 is 4, 4 plus 3 is 7, 7 plus 3 is 10. Root 3 plus root minus root 3 plus root 3 becomes 0. Minus root 2 plus 2 root 2 becomes 0. And so all of this works out to be equal to 10. So this proves that it works out to be 10. That's a solution for this question. Nice and easy, soft. And now finish question 2, and so finish module 2. Now that we finish module 2, we may proceed to module 3. Now we finish module 1, so proceed to module 2. My apologies. Let's get it.